Robots. Robots is the ultimate version of artificial intelligence. The robot is interesting, and it's going to revolutionize a whole slew of new industries, from manufacturing to healthcare. We know that robotic surgery is now able to perform surgeries that we simply can't imagine. However, don't forget that in the future, we're going to have cybernetics. We're going to have robots that are connected to parts of our body. We're going to have little tiny robots that take care of various tasks. Robots, unfortunately, are incredibly hard to do. And the reason for that is because it has to sense the world, which we know how to do now. It has to learn from it and plan and take action, but it has to interact with the world. In the case of a self-driving car, our fundamental goal is collision avoidance. That is a specific objective. In the case of a robot, collision detection is essential. Your goal is to connect, your goal is to collide. How you collide is incredibly difficult to do. There's so many degrees of freedom in all of the joints and fingers and elbows and wrists and torsos of a kinetic object that training it is incredibly difficult. And so recently, some breakthroughs have happened. This is Ada at the Berkeley AI Laboratory, and they've taught Ada how to play hockey. And that right there is probably one of the world's finest AI researchers, and that's what he does for a living. And that's Ada learning repeatedly using reinforcement learning how to play hockey. Now, it turns out that hockey is not too bad. First of all, convincing people to do that for all of your robots as you train it is probably difficult to do. However, remember, that's just hockey. What if we wanted to lift a car? What if we wanted to open the door? What if we wanted to cooperate with a doctor to do surgery? There is no way to have it learn this way, repeatedly in the physical world. And so the answer is this. It turns out we need to create an alternative universe. We need to create an alternate universe. This alternate universe has to obey the laws of physics. In the sense that there's collision detection, it obeys the laws of physics and gravity if you choose. If you choose. It has to be visually photorealistic. It has to look like the world, or these robots can't learn within it. It has to look like the world, it has to sound like the world, it has to behave like the world, and it has to have the ability to learn inside this alternative universe. We have to be inside it as well, so that we could teach it using imitation learning, using all kinds of new deep learning techniques. So it has to be a virtual environment that we could be part of as well. This alternative universe that is visually real, that is physically real, has to have one additional characteristic. It should not follow the laws of time. The only thing that we expected to do is to be hyperspaced. We would need it to train in warp speed. And the reason for that is because there's no reason for us to have to wait around for Ida to learn how to play hockey in the physical world in real time. And so we created a new tool. It's a new world. It's a new simulator we call Isaac. Isaac is named after the two Isaacs. Isaac Newton for physics and Isaac Asimov of AI. We brought the two Isaacs together into this new world we call Isaac. Isaac has the input of environments and robots. So we could put virtual sensors of the robot, we put the virtual actuators and the virtual effectors of the robot into it, and it's connected to OpenAI's OpenAI Gym, where all the reinforcement learnings and all the interesting algorithms that could be applied. We would simulate in this environment and run it on top of any NVIDIA GPUs, and inside that computer is a virtual brain. And when we're done with it, we literally take that virtual brain and put it into a real robot. And this robot wakes up almost as if it was born to know this world, and then the last little bit of domain adaptation that it does is done in the physical world. And so when a robot turns on, it has already been pre-trained, if you will, and it would be pre-trained in the Isaac world. And we, as a company, have the unique capability to bring this capability together. We know how to do physics in super real time. We know how to do amazing computer graphics. We know how to do AI. And so we decided to integrate it all into one thing we call Isaac. So ladies and gentlemen, let's take a look at it. This is Isaac. We import mechanical or the environment into it, and we could train Isaac. Now, in this particular case, Isaac has been trained. And so notice, when Mike moves the puck, when it moves the net, Isaac somehow figures it out. Oh! Now, this all looks wonderful. Okay, this is all in computer graphics. Now, one of the things that we could do is, of course, we could replicate a whole bunch of Isaacs and have them all learn. And then we take the smartest one. And we take the brain out of that smartest one, and we put it in everybody else's brain, and then we say, okay, now start again. And then we figure out which one's the smartest one. And we take that brain, we put it into everybody else's, and we say, start again. And so as a result, we could accelerate the time to learning. Look at all these Isaacs. They're all trying to figure it out. They're all trying to figure it out. And so that's great. Let's take a look at some of the clips from when they were learning. It's got to figure out where the puck is. It's got to see the puck, figure it out. It's got to figure out how hard to hit it. It's got to figure out where to hit it. That's incredible. Now, guys, ladies and gentlemen, Isaac. Well, look, if it can learn how to play hockey, it can surely learn how to play golf. And so here's Isaac learning how to putt. And so let's do it. There's Isaac. Reads the green. Nice. Now, remember this. No programming was done. No programming was done. Isaac just sat there and tried until he figured out how to putt. Okay, not strong enough. Well, let's get, really? Oh, no way. All right, let's give Isaac something hard to do. Let's move. Oh, here it comes. All right. Okay, good job. Thank you very much. Ladies and gentlemen, Isaac. So the next time you guys see Isaac, I hope that Isaac is standing in the middle of a sand bunker, and we'll teach you how to chip out and see if we can sink it. Okay, so Isaac, this is a robotics simulator, the next stage of AI, where you have to sense the world, figure out what you learn from the world, and plan about what you're going to do, take action, sense the results of your action, and you go around in that loop. And we created a simulator that makes it possible for robots to learn inside this virtual world, this alternative universe. And hopefully, as we put this out there, there'll be all kinds of robots that are going to be created, and they'll use reinforcement learning and transfer learning and imitation learning and other forms of learning in order to program these very sophisticated robots. That's it. That was what we talked about today. We talked about two things. We talked about the fact that accelerated computing is really coming to the fore. This is the rise of accelerated computing. Our GPU computing platform has been adopted by high-performance computing scientists all over the world. And recently, with the advent of deep learning and the breakthroughs there, we're now seeing a new era in computing we call the era of AI. Volta is the next generation next giant leap into that new world. We also introduced several things with Volta. One is a brand new instruction set we call the Tensor Core. Second, a full compiler and optimizer for inferencing we call Tensor RT. Between Tensor Core and Tensor RT, not only do we accelerate deep learning, but we also make it possible for hyperscale data centers to deploy deep learning broadly into their data centers without having to build more and more and more data centers. We can save 15 times the cost of deploying deep learning into the world. We introduced DGX-1 and DGX-1 Station. Both of them are open for orders now. We also have the support of every single cloud computing partner in the world. And so you can find the NVIDIA GPUs with all of our software on Alibaba and Amazon and Baidu and Facebook and Google and Microsoft and Tencent. Every single cloud will have this one standard architecture. One of the things that we've done is introduce this idea of a containerized software stack that allows you to use one software stack without having to optimize your computer from premise to cloud. And this way, when you're ready to burst into the cloud, that software stack is already in the cloud registry, it's all fully optimized, and you don't have to reconfigure it. We also announced that we would like to expand the reach of deep learning, to proliferate this capability, to democratize the ability for every single IoT device around the planet, the trillions of them that are going to be able to use deep learning in the future, to be able to access a world-class design. We're going to open source the Xavier DLA design. We're going to continue to advance it, continue to improve it, and people who use it will continue to gain the benefits of it. We also announced two other things. Toyota has now announced their support and creation of their future autonomous vehicles based on the NVIDIA Drive PX platform. And then lastly, we announced the first alternate reality virtual robot simulator so that we can hopefully work together to bring the future of artificial intelligence and robotics to the world. That's all I have today. Thank you guys very much for coming. Have a great GTC. It's great seeing all of you.